Important players in chip production. The global narrative surrounding the semiconductor industry is dominated by a pantheon of household names. We speak of NVIDIA as the architect of the artificial intelligence revolution, capitalizing on the insatiable demand for parallel processing. We recognize TSMC, Taiwan's semiconductor manufacturing company, as the indispensable forge, the foundry where the ethereal designs of Silicon Valley are transmuted into physical reality. We acknowledge ASML, the Dutch engineering marvel, as the sole provider of the lithography tools, the brushes used to paint the future. These entities form the visible peaks of a vast industrial mountain range. Yet beneath these towering summits lies a bedrock of material suppliers, chemical manufacturers, gas purifiers, and substrate engineers, without whom the entire edifice of modern technology would crumble. This review serves as an exhaustive investigation into this subterranean economy. These are companies that operate far from the limelight, often in rural Japanese prefectures or industrial European towns. Their market capitalizations are frequently a fraction of the tech giants they serve, yet their strategic leverage is immense. They operate in markets defined by weaponized interdependence, where extreme specialization has created choke points of such severity that a single factory fire, a localized regulatory change, or a diplomatic spat can paralyze the global production of electronics. The current geopolitical climate has laid bare the fragility of this ecosystem. As nations strive for technological sovereignty, they are discovering that building billion-dollar fabrication plants, or fabs, is merely the first step. A fab is a voracious beast. It must be fed a continuous ultra-pure diet of silicon, photoresists, fluorinated gases, and rare earth minerals. This review argues that the true power in the semiconductor age lies not just with those who design the chips, but with those who possess the alchemical knowledge to create the materials that make them possible. We will explore the roles of companies like Shin-Etsu Chemical, JSR Corporation, Kanto Denka Kogyo, and Ajinomoto, illustrating how the physics of the Angstrom era has concentrated global power into the hands of a few invisible titans. The silicon monolith, Shin-Etsu Chemical, and the canvas of reality. Before a transistor can be patterned, before a logic gate can switch, and before code can be executed, there must be a substrate. The silicon wafer is the fundamental unit of the digital economy. It is the canvas upon which all computation is written. While the world obsesses over the nanometer-sized features printed on the wafer, few appreciate the engineering marvel that is the wafer itself. Dominating this foundational sector is Shin-Etsu Chemical Co. Limited. Based in Tokyo, Shin-Etsu is arguably the most critical company in the semiconductor supply chain that the general public has never heard of. Along with its domestic rival, Sumco Corporation, Japanese firms control the majority of the global market for semiconductor-grade silicon wafers. Recent market analysis indicates that Shin-Etsu and Sumco combined hold a market share exceeding 50%, with Shin-Etsu leading the pack. The manufacturing of a semiconductor-grade wafer is a task of theological purity. The industry standard is 11N purity, 99.999999999% pure silicon. To put this in perspective, if the entire population of the Earth represented the silicon atoms in a wafer, a non-silicon impurity would be equivalent to finding a single specific person. This level of purity is not a luxury, it is a physical requirement. A single impurity atom in the active region of a transistor can cause electron leakage, rendering a chip destined for a supercomputer or an iPhone useless. The dominance of Shin-Etsu is rooted in its mastery of the Czochralski process, a crystal growth method that balances thermodynamics, fluid dynamics, and material science. The process begins with high-purity polycrystalline silicon, which is melted in a quartz crucible at temperatures exceeding 1400 degrees Celsius. A seed crystal, a pencil-sized piece of perfect silicon, is dipped into the molten bath and slowly drawn upwards while rotating. As the seed is withdrawn, the molten silicon solidifies at the interface, mimicking the crystal structure of the seed. This forms a massive single crystal ingot, a massive cylinder that can weigh hundreds of kilograms and measure 300 millimeters in diameter. The engineering challenge is immense. The temperature gradients must be controlled to within fractions of a degree. The rotation speed must be perfectly calibrated to ensure a uniform distribution of dopants, chemicals added to modify electrical properties, and to control the oxygen content derived from the quartz crucible. Shin-Etsu's specific competitive advantage lies in its proprietary tweaks to this process. As the industry moves toward 2 nanometer nodes, the flatness and defect density of the wafer become critical. Shin-Etsu has developed specialized annealing processes, heating the wafer in a controlled atmosphere to eliminate microscopic crystal voids known as crystal-originated particles, or COPs. Furthermore, they have mastered the production of epitaxial wafers, where a pristine layer of silicon is grown on top of a standard polished wafer, providing a defect-free surface for the most advanced logic processors. The economic gravity of Shin-Etsu is substantial. The global semiconductor materials market was valued at nearly $70 billion in 2024, with wafers representing the largest segment. Shin-Etsu's aggressive capital expenditure ensures its continued dominance. In 2024, the company announced a new lithography materials plant in Japan with an investment totaling approximately $560 million, further entrenching its domestic production base. This concentration constitutes a hard choke point. While a software company can be replicated with talent and servers, a silicon wafer manufacturer requires decades of institutional knowledge and billions in capital equipment. If Shin-Etsu were to halt production, there is no idle capacity in the world that could replace it. Competitors like Global Wafers in Taiwan and Siltronic in Germany exist, but they operate at full capacity and often lag in the yield rates for the most bleeding-edge specifications. Thus, the factories of Intel in Oregon, TSMC in Taiwan, and Samsung in Pyeongtaek are all tethered to the output of Shin-Etsu's furnaces. The lithography oligopoly, JSR, TOK, and the chemistry of light. If the silicon wafer is the canvas, the photoresist is the paint. Photolithography is the process by which circuit patterns are transferred onto the wafer. A light-sensitive chemical, photoresist, is spun onto the wafer, which is then exposed to light through a mask. The light changes the chemical solubility of the resist, allowing the unexposed or exposed areas to be washed away, creating a stencil for etching. The photoresist market is an oligopoly dominated by Japanese firms who collectively control between 70 and 90% of the global supply. The key players are JSR Corporation, Tokyo Oka Kogyo, TOK, Shin-Etsu Chemical, and Fujifilm Electronic Materials. This sector is characterized by extreme chemical complexity. Modern photoresists are not single chemicals, but cocktails of polymers, photoacid generators, PAGs, quenchers, and solvents, each balanced to interact with specific wavelengths of light. Among the titans, JSR Corporation has distinguished itself by betting heavily on the future, extreme ultraviolet lithography, EUV. As the industry transitioned from deep ultraviolet light, DUV 193 nanometer wavelength to EUV 13.5 nanometer wavelength to print features smaller than 7 nanometers, the physics of photoresist broke down. EUV photons are high energy but scarce. The resist needs to be incredibly sensitive to capture the image, but robust enough to withstand the subsequent etching. JSR cemented its leadership by acquiring Inpria, an Oregon-based startup that pioneered metal oxide resists, MORE. Traditional resists are carbon-based polymers. However, at the atomic scale of 2 nanometer chips, carbon polymers are too large and fluffy, leading to rough edges, line edge roughness, that ruin the chip's performance. Inpria's technology uses tin oxide clusters, essentially tiny metal balls that absorb EUV light far more efficiently and allow for sharper patterns. By integrating Inpria's technology, JSR has positioned itself as the gatekeeper to the Angstrom era. Intel, Samsung, and TSMC cannot ramp up their 2 nanometer and 1.4 nanometer nodes without the high absorption resists that JSR provides. This technological moat is deeper than mere market share. It is a fundamental material science advantage that competitors struggle to replicate without infringing on a thicket of patents. While JSR pushes the boundaries of physics with metal oxides, Tokyo Oka Kogyo serves as the backbone of the industry's volume production. TOK holds the top global market share for semiconductor photoresists overall, accounting for approximately 25% of the market. TOK's strength lies in its breadth. While the headlines focus on AI chips, the global economy runs on legacy chips, the microcontrollers in cars, the power management ICs in washing machines, and the sensors in medical devices. These chips are made using older lithography standards like G-line, I-line, and KRF, krypton fluoride. TOK commands a 32.4% share of the KRF market and a 22.7% share of the G/I-line market. However, TOK is not merely a legacy player. They also command a 28% share of the EUV photoresist market, competing directly with JSR and Shin-Etsu. This dual dominance makes TOK a systemic entity. A disruption at TOK would not only delay the next NVIDIA GPU, but would also halt the production of Toyota Camrys and Sony PlayStations. Fujifilm Electronic Materials completes the Japanese quartet. Having successfully pivoted from photographic film, which relies on silver halide chemistry, to semiconductor materials, which relies on polymer chemistry, Fujifilm has become a one-stop shop for the industry. Their strategy involves bundling photoresists with other critical materials like CMP slurries and developers. Fujifilm's recent investments underscore the sector's growth. They have committed billions of yen to expand production facilities in Shizuoka, Japan, and have established advanced manufacturing sites in Taiwan and the US to be closer to TSMC and Intel. Their wave control mosaic technology for image sensors, using colored resists to filter light for camera chips, is another niche where they hold a dominant position, essentially controlling the quality of every smartphone camera on the market. The strategic vulnerability of the photoresist supply chain cannot be overstated. Unlike silicon wafers, which are chemically stable, photoresists are perishable. They have a limited shelf life, often 3 to 6 months, and must be stored at controlled temperatures. This means they cannot be stockpiled in vast strategic reserves like oil or grain. The supply chain is a continuous, living flow from the chemical reactors in Japan to the spin coaters in Taiwan and the US. This just-in-time dependency creates a fragile tether. If a major earthquake were to hit the Chubu or Kanto regions of Japan, where much of this production is clustered, the global supply of photoresist would dry up within months. The fabs would have no paint for their canvas, and production would cease. The gas giants, nitrogen, neon, and the air we etch with. While lithography defines the pattern, etching defines the structure. Etching is the process of removing material to create the 3D structures of a chip, such as the deep trenches of a 3D manned memory cell. This process relies on highly reactive halogen gases, particularly fluorine-based compounds. Kanto Benka Kokyo is a company that exemplifies the invisible Titan archetype. It is a dominant player in the market for high-purity etching and cleaning gases, specifically nitrogen trifluoride, tungsten trifluoride, and chlorine trifluoride. NF3 is the workhorse cleaning gas of the industry. After a deposition step, the vacuum chambers of semiconductor tools are coated in residue. NF3 is injected to turn it into a gas that can be pumped away. Without NF3, the tools would become dirty and unusable within hours. Kanto Denka holds a massive market share in this specific gas, particularly in the high-purity grades required for logic and memory manufacturing. The fragility of this dominance was starkly illustrated by a fire at Kanto Denka's NF3 plant in Shibukawa City, Gunma Prefecture. Because Kanto Denka holds over 90% of the domestic Japanese share and is a key supplier to Samsung, Kioxia, and Sony, the fire threatened to choke off the supply of cleaning gas to the world's major memory makers. Unlike industrial-grade gases, semiconductor gases must be purified to 6 nines, 99.99999%, or higher. You cannot simply switch suppliers overnight. Qualifying a new gas source takes 6 months to a year. This incident highlighted how a single industrial accident in a Japanese town could threaten the global supply of flash memory. Perhaps no event has better illustrated the intersection of geopolitics and material supply than the neon crisis triggered by the Russian invasion of Ukraine. Neon is a noble gas used in excimer lasers, argon fluoride and krypton fluoride, the light sources for lithography scanners. In the gas mixture of these lasers, neon acts as a buffer, constituting over 95% of the volume. It mediates the electrical discharge and protects the laser optics from the violent reactivity of fluorine. Prior to 2022, Ukraine was responsible for approximately 50% of the world's commercial neon supply and, critically, nearly 90% of the semiconductor-grade neon imported by the United States. This dominance was a historical accident of the Soviet command economy. Neon is a byproduct of air separation units, ASUs, used in steel manufacturing. The Soviet Union built massive steel plants in Ukraine, such as Azovstal in Mariupol, equipped with ASUs capable of capturing rare gases like neon, krypton, and xenon. When Russia invaded Ukraine in February 2022, 2 primary neon purification companies, Cryon in Odessa and Ingas in Mariupol, were forced to halt operations. Ingas was located in the heart of the siege of Mariupol, one of the most intense battlegrounds of the war. Cryon suspended operations due to the bombardment of Odessa. The impact was immediate. The price of neon, which had already spiked 600% during the 2014 annexation of Crimea, surged again. The semiconductor industry, which had failed to sufficiently diversify after the 2014 warning, faced a panic. Companies like TSMC and ASML scrambled to secure supplies from China and to develop recycling technologies to recapture neon from their laser systems. The neon crisis serves as a stark reminder of the long tail of the supply chain. The most advanced chips in the world, powering U.S. stealth fighters and AI data centers, were dependent on a byproduct gas from Soviet-era steel mills in a war zone. While the industry has since moved to diversify, with companies like Lind expanding capacity in Texas and South Korea, the structural reliance on obscure byproducts remains a systemic risk. Rounding out the gas sector is Taiyo Nippon Sanso, Japan's largest industrial gas producer and a top-tier global player alongside Lind, UK/Germany, Air Liquide, France, and Air Products, USA. Taiyo Nippon Sanso commands roughly 40% of the Japanese industrial gas market and is integral to the supply of bulk gases, nitrogen, hydrogen, oxygen, and argon, as well as specialty electronic gases. Their role is critical in the inerting of fabs. Semiconductor manufacturing must occur in an oxygen-free environment to prevent oxidation of the copper interconnects. Taiyo Nippon Sanso provides the endless stream of ultra-pure nitrogen that blankets every wafer as it moves through the factory. Their dominance in the Asian market puts them at the heart of the manufacturing hubs in Taiwan, Korea, and Japan. The liquid precision, Resonac, Fujimi, and CMP slurries. As a chip is built layer by layer, the surface becomes uneven. To add the next layer of lithography, the surface must be perfectly flat. This is achieved through a process called chemical mechanical planarization, CMP. The wafer is pressed face down against a rotating pad and flooded with a slurry, a liquid containing abrasive nanoparticles and chemical etchants. This is a process of brutal elegance, chemically softening the surface while mechanically sanding it away, stopping with angstrom-level precision. If the polishing is too aggressive, it scrapes away the copper wiring, dishing. If it is too gentle, it leaves short circuits. Resonac Holdings Corporation, formed from the merger of Showa Denko and Hitachi Chemical, is a titan in this space. They produce the specialized slurries required for polishing copper, tungsten, and dielectric layers. Resonac's dominance is built on the formulation of these slurries. The abrasive particles, often silica or ceria, must be perfectly uniform in size. A single rogue particle that is slightly larger than the rest will scratch the wafer, creating a killer defect that destroys the chip. Resonac controls the chemistry of the additives that protect the lower layers while the upper layers are removed. Beyond slurries, Resonac is a powerhouse in packaging materials, which we will explore later. Their scale allows them to weather the high R&D costs associated with developing new slurry formulations for each new node, such as polishing cobalt or ruthenium interconnects for 2-nanometer chips. The barrier to entry in CMP slurries is deceptively high. It is not just about mixing grit into water. It is about colloidal science, keeping billions of nanoparticles suspended in a solution without clumping together or agglomerating during transport or storage. If the slurry settles or clumps, it becomes useless. This requires specialized filtration and stabilization chemistry that companies like Resonac, Fujimi Corporation, and the US-based Cabot Microelectronics, now Integris, have mastered over decades. The packaging monopoly, Ajinomoto Build-Up Film, ABF. In the annals of industrial history, there are few pivots as surprising as that of the Ajinomoto Group. Known globally for its food products and specifically for the commercialization of monosodium glutamate, MSG, Ajinomoto is also the holder of a near monopoly on a material without which high-performance computing would cease to exist: Ajinomoto Build-Up Film, ABF. The story begins in the 1990s. As CPUs became more powerful, the number of input-output connections, the pins that connect the chip to the motherboard, exploded. Traditional packaging materials, which were liquid-based, dried too slowly and unevenly to handle the complex, multi-layered wiring required to route these connections. Ajinomoto researchers, leveraging their expertise in amino acid chemistry, the basis of MSG, developed a thermosetting film that provided perfect insulation, high durability, and low thermal expansion. This film allowed substrate manufacturers to build up layers of microscopic wiring, routing the nanometer-scale connections of the silicon die to the millimeter-scale connections of the printed circuit board. Today, ABF is the de facto standard for high-performance CPU and GPU substrates. Whether it is an Intel Core processor, an AMD Ryzen, or the NVIDIA H100 GPUs powering the latest AI models, the packaging substrate almost certainly uses ABF. Market estimates suggest Ajinomoto holds a global market share approaching 100% for this specific class of high-end build-up film. This monopoly creates a singular bottleneck. During the COVID-19 pandemic, a global shortage of semiconductors was exacerbated by a specific shortage of ABF substrates. Lead times for these substrates extended over 50 weeks. The shortage wasn't of silicon, but of the thin amino acid-based film required to package the silicon. As the industry pivots to artificial intelligence, the importance of ABF has only grown. AI chips are massive. They require huge substrates with dozens of layers of ABF to route the massive bandwidth of data between the GPU and the high bandwidth memory, HBM. Consequently, the supply of ABF is now directly correlated with the deployment of AI infrastructure. Ajinomoto has become as critical to the AI ecosystem as TSMC or NVIDIA, yet it sits quietly in the background, a food company holding the keys to the future of computing. The pellicle and the mask. Mitsui Chemicals. In the EUV lithography process, the mask, or reticle, is the master blueprint of the chip. It is a mirrored plate containing the circuit pattern. Because EUV light is so easily absorbed, the mask cannot be covered by a traditional glass protective cover. It must be exposed to the vacuum of the scanner. However, any speck of dust that lands on the mask will block the light and be printed onto every single chip, destroying the yield. To solve this, the industry uses a pellicle, an ultra-thin membrane that hovers just above the mask. It catches the dust, keeping it out of the focal plane so it doesn't print. Making an EUV pellicle is one of the hardest material science challenges in the world. The membrane must be incredibly thin, tens of nanometers, to allow the EUV light to pass through, transmittance, but strong enough to withstand the immense heat generated by the EUV laser, thermal load, and the mechanical stress of the scanning motion. Mitsui Chemicals has emerged as the leader in this esoteric field. They are the primary licensed supplier of ASML's EUV pellicles. The material is typically a polysilicon-based membrane, though the industry is moving toward carbon nanotubes, or CNTs, for higher transmission. Mitsui's dominance here is another choke point. Without these pellicles, mass production of EUV chips becomes economically unviable due to yield losses from particle contamination. The solvents of precision. Tri-chemical laboratories. The high-K precursors. As transistors shrink, the gate oxide, the insulation layer that controls the flow of electrons, becomes too thin to stop electrons from tunneling through, leaking. To fix this, the industry switched to high-K dielectrics, materials with a high dielectric constant, like hafnium oxide and zirconium oxide. Tri-Chemical Laboratories is a niche Japanese supplier that specializes in the chemical precursors used to deposit these high-K layers. These are not commodity chemicals. They are complex organometallic compounds that must be volatile enough to turn into gas for atomic layer deposition, ALD, but stable enough to be transported. Tri-Chemical's business model is extreme specialization. They produce small batches of incredibly difficult to synthesize chemicals. Their CVD precursors are injected into vacuum chambers to grow films one atomic layer at a time. Without their specific hafnium or zirconium compounds, modern logic and memory chips would simply leak charge, overheat, and fail. The company focuses on the niche of the niche, ensuring that for specific atomic layers, they are the only viable option in the world. Geopolitics and weaponized interdependence. The theoretical risk of these material choke points became a practical reality in July 2019 during a trade dispute between Japan and South Korea. Stemming from historical grievances regarding wartime labor, the Japanese government imposed export restrictions on 3 key semiconductor materials destined for South Korea: fluorinated polyamide, photoresist, and high-purity hydrogen fluoride, HPHF. The restriction on hydrogen fluoride was particularly devastating. HPHF is used for etching and cleaning wafers. At the time, Japanese firms like Stella Chemifa and Morita Chemical Industries produced over 70% of the world's HPHF, and more importantly, nearly 90% of the supreme purity grades required by Samsung and SK Hynix. The impact was immediate. South Korean chip makers faced a crisis. They could not simply switch to Chinese or domestic HF because the purity was insufficient. Even a deviation of parts per billion in impurity levels could crash the yield of a DRAM line. The dispute forced South Korea to scramble for localization, investing billions to prop up domestic supplier Solbrain. While Solbrain eventually succeeded in producing high-purity HF, the transition was painful and slow, demonstrating the stickiness of the supply chain. Japan's dominance in these materials allowed it to throttle the manufacturing engines of a major economic rival with bureaucratic ease. Another form of disruption emerged in 2022, not from trade war, but from environmental regulation. The 3M plant in Zwijndrecht, Belgium, was responsible for 80% of the global production of semiconductor coolants, PFAS-based fluids used to cool etching equipment. When the Belgian government ordered the plant to shut down due to PFAS contamination concerns, the global industry faced a coolant crisis. Major fabs like TSMC and Intel were notified of imminent shortages. The industry realized that while it had diversified its silicon and tool supply, it had allowed the supply of essential coolants to concentrate in a single factory in Belgium. This event highlighted the collision course between the semiconductor industry, which relies on toxic exotic chemicals, and the growing momentum for environmental protection, ESG. As PFAS regulations tighten in Europe and the US, this green choke point remains a persistent threat. This concentration of power in the hands of invisible titans creates a global system of weaponized interdependence. A seismic event in Tokyo, a factory fire in Gunma, or a regulatory ruling in Brussels can halt the production of data centers in Virginia and assembly lines in Shenzhen. As we advance into the era of AI and ubiquitous computing, the stability of our future depends not just on the visible giants of tech, but on the silent, steady flow of chemicals from the suppliers we have never heard of. The Fabricators, mastering the atom. The manufacturing of a modern semiconductor is arguably the most complex industrial process in human history. It takes place within the sterile confines of a fabrication plant, or fab, where silicon wafers travel through hundreds of distinct process steps over a period of months. This sector is dominated by a powerful oligopoly of equipment manufacturers, each holding critical choke points in the production line. Among them, 3 US-based giants stand out: Applied Materials, Lam Research, and KLA Corporation. Applied Materials, AMAT, stands as the largest and most diversified player in the semiconductor equipment space. With a market capitalization exceeding $200 billion and a workforce of approximately 36,000 employees, the company acts as the general store for the fab, supplying tools for almost every step of the manufacturing process except lithography. Its dominance, however, is most profound in the realm of deposition, the additive process of layering materials onto a silicon wafer. Applied Materials defines itself not merely as a tool maker, but as a materials engineering company. Modern chips are complex 3D structures composed of alternating layers of conductors, insulators, and semiconductors, transistors. Applied Materials provides the technology to create these layers with atomic precision. The company generated $26.5 billion in revenue in 2023, a figure that underscores its indispensable role in the global supply chain. Unlike competitors that may focus on a single niche, Applied Materials holds a market share of approximately 19 to 21% of the total semiconductor equipment market, giving it a unique, holistic view of the manufacturing flow. This dominance is rooted in its mastery of various deposition techniques. Physical vapor deposition, PVD, uses sputter to thin films of metal, such as copper for interconnects or tungsten for contacts. Chemical vapor deposition, CVD, uses chemical reactions to deposit insulating layers. Atomic layer deposition, ALB, is the most precise of all, adding material one atomic monolayer at a time, a capability that is becoming essential as features shrink to sizes where a single stray atom can constitute a defect. The technological leadership of Applied Materials is embodied in its equipment platforms. The Endura platform, launched in 1990, remains the most successful metallization system in the history of the industry. The genius of the Endura design lies in its vacuum integrity. It operates as a factory within a factory, featuring a multi-chamber architecture where wafers are moved robotically between different process stations without ever breaking the vacuum seal. This is critical because at the nanoscale, exposure to the oxygen in the air can instantaneously create an insulating oxide layer on a metal contact, ruining the electrical connection. The Endura platform has processed the vast majority of microchips made in the last 2 decades, handling everything from aluminum and copper interconnects to underbump metallization for packaging. While Endura rules PVD, the Centura platform, introduced in 1992, became the workhorse for CVD and etch processes, designed with larger facet sizes to support the bulky chambers required for high-temperature epitaxy and high-density plasma CVD. However, the complexities of the AI era required a new approach. In a major strategic shift, Applied Materials recently introduced the Vistara platform, described as its most significant platform innovation in over a decade. Vistara is designed to address the chaotic complexity of modern manufacturing. It hosts an unprecedented variety of chamber types and sizes, allowing for the combination of deposition and etch steps in a single system. Crucially, Vistara is an intelligent platform. It is configured with thousands of sensors that feed massive amounts of real-time data into the company's AIPX software platform. This allows for the monitoring of energy consumption, particle generation, and process drift in real time, enabling fabs to improve yield and sustainability simultaneously. This shift toward AI-integrated hardware demonstrates that Applied Materials is not just building tanks for chemical reactions, it is building data-generating edge devices. The financial engine of Applied Materials is robust, reflecting its scale. In 2024, the company invested $3.23 billion in research and development, a 4.22% increase from the previous year. This enormous R&D budget acts as a formidable economic moat. For a competitor to displace Applied, they would not only need to engineer a better tool, but also replicate decades of accumulated materials science data. The company maintains a healthy gross margin profile, often hovering near 48 to 49%, and a return on equity, or ROE, of over 34%, indicating highly efficient use of shareholder capital. If Applied Materials is the painter adding layers to the canvas, Lam Research is the sculptor, removing material to create form. Lam Research is the undisputed global leader in etching, controlling approximately 45% of the market. As chip architectures have shifted from planar or 2D designs to vertical 3D structures, such as 3D NAND flash memory and FinFET transistors, the importance of etching has skyrocketed, propelling Lam Research to the forefront of the industry. The rise of Lam Research is inextricably linked to the rise of 3D NAND. In modern storage memory, cells are not laid out flat but are stacked vertically, layer upon layer, like a skyscraper. To connect these layers, manufacturers must drill microscopic holes, known as channel holes or high aspect ratio contacts, through the entire stack. This stack can consist of over 100 alternating layers of oxide and nitride materials. The challenge is geometric. The hole must be perfectly straight and uniform from the top of the stack to the bottom. If the etch tilts by even a fraction of a degree, the bottom of the hole will miss its target, rendering the memory cell useless. This process is analogous to drilling a hole the width of a human hair through a 3-story building and hitting a dinner plate in the basement. Lam's tools, such as the Kiyo and Flex process modules, utilize high-density plasma to accelerate ions straight down into the wafer, carving out these features with unparalleled precision. As feature sizes shrink, the physics of etching becomes more difficult. Traditional etching relies on chemical reactions that can inadvertently attack the sidewalls of the hole, leading to a bowing effect that destroys the device structure. To combat this, Lam Research has pioneered cryogenic etching. By cooling the wafer to ultra-low temperatures inside the chamber, the chemical reactivity on the sidewalls is inhibited, while the ions continue to bombard the bottom of the hole. This results in a perfectly vertical profile, a capability that is essential for the next generation of high aspect ratio 3D NAND and logic devices. Furthermore, the transition to gate-all-around transistors requires a new level of finesse known as isotropic selective etch. In a gate-all-around transistor, the gate material must wrap entirely around silicon nanosheets. To achieve this, sacrificial layers between the nanosheets must be removed without damaging the silicon itself. Lam's selective etch product family, Argos, Prevos, and Celis, utilizes novel chemistries to remove specific materials in all directions, isotropically, with angstrom-level precision, ensuring that the delicate nanosheets remain intact. This ability to chemically sculpt the transistor at the atomic level differentiates Lam from competitors who rely primarily on directional plasma bombardment. Recognizing the need for higher productivity, Lam introduced the Sense.I platform. Evolved from the Kiyo and Flex modules, Sense.I features a revolutionary compact architecture that delivers a 50% improvement in etch output density, a critical metric for fabs where floor space is expensive real estate. Like Applied's Vistara, Sense.I is self-aware. It utilizes equipment intelligence technology and machine learning algorithms to capture and analyze data, allowing the tool to autonomously calibrate itself and minimize process variations. This capability reduces downtime and labor costs, addressing the operational efficiency needs of high-volume manufacturers. Lam Research demonstrates exceptional financial health, often outperforming peers in profitability metrics. With an ROE of over 54% and a net margin that has historically hovered around 25 to 30%, Lam is a highly efficient profit generator. The company's focus on the etch and deposition segments allows it to maintain deep technical specialization. In 2024, Lam invested roughly $1.9 billion in R&D, a 10% increase year over year, reflecting its commitment to solving the complex challenges of the 3D era. While its heavy exposure to the memory market can lead to cyclical volatility, it also positions Lam as a primary beneficiary of the AI-driven demand for high-bandwidth memory, HBM, and enterprise SSDs. In the high-stakes world of semiconductor manufacturing, visibility is synonymous with viability. KLA Corporation dominates the market for process control and yield management. While Applied Materials and Lam Research build the chip, KLA ensures that it actually works. They provide the inspection and metrology tools that find defects and measure critical dimensions, enabling fabs to ramp up production yields and maximize profitability. The semiconductor industry is driven by yield, the percentage of functional chips on a wafer. At the start of a new process node, yields can be notoriously low, sometimes in the single digits. KLA's business model is predicated on helping fabs identify the root cause of these failures. Because a 1% improvement in yield can translate to tens of millions of dollars in additional profit for a manufacturer like TSMC or Intel, KLA enjoys immense pricing power. This is reflected in its gross margins, which consistently exceed 60%, significantly higher than its peers in the deposition and etch segments. KLA's dominance is built on a portfolio that spans the electromagnetic spectrum. The company's flagship tools utilize broadband plasma optical inspection. Systems like the 2965 and 3900 series use incredibly bright, broad-spectrum light sources, brighter than the sun, to scan wafers at high speed. These tools act as the fab's radar, quickly identifying surface defects, particles, and scratches across high volumes of wafers. However, as features shrink below the wavelength of light, optical inspection faces physical limits. To see the smallest defects, KLA deploys E-beam inspection tools like the EDR7380. Electrons have a much shorter wavelength than photons, allowing these tools to resolve defects down to the nanometer scale. Crucially, E-beam tools can detect voltage contrast defects, electrical shorts or opens buried deep within the 3D structure of the chip that are invisible to optical tools. The trade-off is speed. Optical inspection is fast, taking about an hour to scan a wafer, whereas E-beam inspection is historically up to 1,000 times slower. Consequently, fabs use a hybrid strategy. Optical tools scan the entire wafer to map hotspots, and E-beam tools are then guided to those specific coordinates for deep dive analysis. KLA's mastery of both technologies and the software that links them creates a high barrier to entry. Beyond finding defects, KLA excels at metrology, the science of measurement. As the industry moves to gate-all-around transistors, the need for precision measurement explodes. KLA's tools must measure the thickness of nanosheets and the alignment of layers, or overlay, with sub-angstrom accuracy. The 2965 tool, for example, utilizes enhanced broadband plasma illumination and superpixel mode to capture critical defects in nanosheet logic nodes. This capability is supported by AI-driven algorithms that help distinguish between nuisance defects, which don't kill the chip, and killer defects, a critical distinction in the noisy environment of a 3-nanometer process. In fiscal year 2025, KLA's R&D spending reached approximately $1.4 billion, ensuring that its eyes remain sharp enough to see the atomic-scale features of the future. The company's services revenue also provides a steady stream of cash flow, as its complex tools require constant maintenance and calibration to function at the bleeding edge. The architects, defining the logic. While the equipment giants manipulate the physical world, ARM Holdings defines the logical rules by which chips operate. ARM does not manufacture chips. Instead, it licenses its instruction set architecture, ISA, and core designs to other companies. This asset-light model has allowed ARM to become the most ubiquitous architecture in history, powering virtually every smartphone on the planet. Recently, however, ARM has launched an aggressive campaign to conquer the data center, challenging the long-held dominance of the x86 architecture. For decades, ARM was synonymous with mobile computing. Its reduced instruction set computing, RISC, architecture was prized for its energy efficiency, making it the only viable choice for battery-powered devices. In contrast, the data center was the fortress of Intel and AMD, whose complex instruction set computing, CISC x86 chips, offered superior raw performance at the cost of higher power consumption. The landscape changed with the rise of cloud computing and hyperscalers like Amazon AWS, Microsoft Azure, and Google GCP. These companies operate millions of servers and face massive electricity bills. They began to prioritize performance per watt and core density over raw single-threaded speed. ARM's architecture, born from the constraints of a battery, proved ideally suited for this new paradigm. By licensing ARM's Neoverse platform, hyperscalers could build custom chips like AWS Graviton, Google Axion, and Microsoft Cobalt that were optimized for their specific workloads, cutting out the profit margin traditionally paid to Intel. Emboldened by these wins, ARM has set a staggering goal to capture 50% of the data center CPU market. This ambition is supported by the AI boom. AI training and inference are incredibly energy-intensive. ARM CEO Rene Haas has warned that without a shift to more efficient architectures, AI data centers could consume up to 25% of the US power grid by the end of the decade. This energy bottleneck serves as a massive tailwind for ARM. The NVIDIA Grace CPU, designed to pair with Blackwell GPUs for AI supercomputing, is built on ARM architecture, proving that ARM can compete at the absolute highest tier of performance. ARM's financial engine runs on two tracks: licensing, upfront fees, and royalties, a percentage of every chip sold. The transition to the data center and the new ARM v9 architecture has significantly boosted this model. The v9 architecture, which includes advanced features for AI and security, commands royalty rates roughly double that of the previous v8 generation. Because complex data center chips utilize large amounts of ARM IP, they generate significantly higher revenue per unit than smartphone chips. This financial leverage is evident in ARM's R&D spending, which surged by nearly 75% to approximately $2 billion in 2024 as the company pivoted aggressively toward high-performance computing designs. This investment is necessary to maintain the Neoverse roadmap, ensuring that ARM cores remain competitive with the best x86 designs from Intel and AMD. The Draftsmen, software defining hardware. Between the architectural vision of ARM and the physical fabrication by Applied Materials lies the essential layer of electronic design automation, EDA. Designing a modern chip, which may contain 50 billion transistors, is beyond human capability. It requires sophisticated software that can synthesize logic, route billions of wires, and verify that the chip will work before it is ever manufactured. This market is a duopoly, dominated by Synopsys and Cadence Design Systems, who collectively control approximately 75% of the market. The fundamental driver of the EDA industry is the astronomical cost of failure. Creating the mask set, the master template used for lithography at a leading-edge node like 3 nanometers, can cost over $500 million. If a design has a bug, that money is incinerated and the product launch is delayed by months. Therefore, chips must be verified virtually to near perfection. Synopsys and Cadence provide the tools that allow this digital verification. Synopsys is often viewed as the leader in digital implementation. Their flagship tool, Fusion Compiler, is the industry standard for synthesizing logic gates and optimizing the place and route of transistors. Synopsys also holds a dominant position in interface IP, selling pre-verified blocks for standards like USB and PCI Express. Cadence has historically held the crown in analog and custom design with its Virtuoso platform, which is ubiquitous for designing the sensitive analog circuits that interface with the real world. Cadence is also a leader in hardware emulation with its Palladium supercomputers, which allow software developers to run code on a simulated version of the chip before the silicon is even fabricated. The most significant trend in EDA is the expansion beyond circuit design into multi-physics simulation. As chips are stacked vertically, 3D IC, and pushed to their thermal limits, designers can no longer ignore the physical effects of heat, stress, and electromagnetism. A chip might function logically, but if it melts or warps due to heat, it is a failure. This necessity drove Synopsys to acquire Ansys, the global leader in engineering simulation, in a massive $35 billion deal. Ansys provides the software used to simulate jet engines and bridges. Bringing this capability into chip design allows Synopsys to offer a silicon-to-systems digital twin. Engineers can now simulate how a chip will behave thermally within its package, on the circuit board, and inside the final device chassis. Cadence has responded with its own aggressive expansion into simulation, acquiring Beta KE for $1.24 billion to bolster its structural analysis capabilities. They also launched the Millennium platform for fluid dynamics acceleration. This arms race indicates that the definition of EDA is expanding. It is no longer just about placing transistors, it is about simulating the entire physical reality of the electronic system. Both companies are utilizing AI to revolutionize productivity. Synopsys' DSO.ai and Cadence's Cerebrus use reinforcement learning to automatically explore the design space. A human engineer might try 10 different ways to arrange components to minimize power. An AI can run thousands of iterations overnight, finding non-intuitive layouts that reduce power consumption by 10 to 20% and improve productivity by 3x. As chip complexity outpaces the supply of engineering talent, these AI tools are becoming mandatory for staying on the curve of Moore's Law. Financially, both companies operate with the software industry's enviable economics. They invest roughly 35% of their revenue back into R&D, a figure far higher than most hardware companies, to maintain their technological lead. Their subscription-based models provide recurring revenue visibility, shielding them from the cyclical volatility that affects the equipment manufacturers. The building blocks, the IP economy. In the early days of semiconductors, companies designed every part of the chip themselves. Today, the complexity is too high. A system on chip, or SoC, is assembled like a puzzle, using pre-verified blocks of intellectual property, or IP, for standard functions like memory interfaces, Wi-Fi, or high-speed data links. This IP economy allows chip designers to focus on their secret sauce, like AI cores, while buying the rest from specialists. Rambus, once known primarily for its litigious defense of patents, has transformed into a critical product company. They dominate the market for the physical interface chips required for high-speed memory, specifically DDR5 and HBM, or high-bandwidth memory. As data centers upgrade to DDR5 memory to feed hungry AI processors, the physics of signaling becomes difficult. The memory modules require specialized chips called register clock drivers, or RCDs, to maintain signal integrity at high speeds. Rambus holds roughly 40 to 50% of this market, effectively acting as a toll collector on the memory upgrade cycle. Their recent extension of a patent license agreement with Micron through 2029 highlights the stability of their position. Major memory manufacturers rely on Rambus IP to build their products legally and technically. As AI chips become faster, the bottleneck often shifts to moving data between chips. This is the domain of Alpha Wave Semi, a leader in high-speed connectivity IP known as SerDes. SerDes blocks are the gateways that allow data to enter and exit a chip at blinding speeds, currently reaching up to 224 gigabits per second per lane. AlphaWave is positioning itself as a leader in the chiplet ecosystem. As chips get too large to manufacture in one piece, they are being broken into smaller dies, chiplets, connected by high-speed links. AlphaWave provides the Universal Chiplet Interconnect Express IP that enables this communication. Their interdependence with the manufacturing ecosystem is profound. AlphaWave was named TSMC's OIP Partner of the Year for 2025, underscoring that the foundry cannot sell its advanced packaging services without high-quality connectivity IP to make the package work. Convergence, a case study in interdependence. To fully understand how these companies rely on one another, one must examine a specific technological inflection point: Backside Power Delivery Network, BSPDN. This technology, slated for widespread adoption at the 2nm node 2025 to 2026, involves moving the power wires from the front of the chip, where they compete with signal wires, to the back of the silicon wafer. This single shift triggers a cascade of requirements across the entire ecosystem, illustrating the forced cooperation of the industry. The chip logic must be designed with BSPDN in mind. The standard cells, the fundamental building blocks of logic, must be re-architected to accept power from below rather than above. ARM optimizes its latest cores, such as the Cortex-X series, to leverage the area savings that BSPDN provides, allowing for denser and more efficient layouts. Traditional routing software assumes power comes from the top. Synopsys and Cadence must rewrite their place and route algorithms to handle two-sided routing. Furthermore, burying power rails deep in the silicon changes how heat dissipates. Designers must use the new ANSYS and Synopsys or Cadence and Beta CAE multi-physics tools to simulate these new thermal realities before the chip is built. To connect the backside power to the transistors on the front side, manufacturers must drill nano-through-silicon vias through the silicon substrate. These holes are incredibly tiny and deep. Lam Research provides the specialized etching tools capable of creating these high aspect ratio vias without damaging the active transistor layers. Once the via is etched, it must be filled with metal, usually tungsten or molybdenum, to conduct electricity. Applied Materials uses its Endura platform to deposit these metals with zero voids. If there is a single air pocket in the via, the resistance will spike and the chip will fail. The precision of Applied's metal deposition is the difference between a working chip and a piece of scrap. Inspecting these connections is a nightmare because they are buried under the silicon. KLA must develop new acoustic or high-voltage E-beam techniques to see through the wafer and verify that the backside power rails are aligned perfectly with the front-side transistors. Without KLA's eyes, the fab is flying blind. No single company can implement BSPDN alone. If Synopsys software can't model it, ARM can't design it. If Lam can't etch the via, AMAT can't fill it. If KLA can't inspect the alignment, TSMC can't sell the wafer. This interdependence locks these companies into a shared roadmap where they must synchronize their R&D efforts years in advance. The high-stakes R&D and financial moats. The glue that holds this ecosystem together and the barrier that keeps competitors out is the sheer scale of research and development, R&D. The cost of staying relevant in the semiconductor industry is astronomical, creating a formidable economic moat around the incumbents. In 2024, the R&D spending of these giants reached stratospheric levels. Applied Materials invested approximately $3.2 billion to push the boundaries of materials engineering. Lam Research spent roughly $1.9 billion to refine its etch and deposition technologies. KLA Corporation poured about $1.4 billion into keeping its inspection tools sharp enough to see the atomic scale. On the design side, ARM Holdings saw its R&D spending surge by nearly 75% to approximately $2 billion as it pivoted to the data center. Synopsys and Cadence consistently invest about 35% of their revenue back into R&D, a percentage that dwarfs the R&D intensity of most other industries. This spending buys more than just new products. It buys accumulated knowledge. For a new startup to compete with Lam Research in etching, they would not just need $1 billion, they would need 30 years of accumulated data on plasma physics, surface chemistry, and chamber dynamics. They would need the trust of customers who cannot afford to risk a $20 billion fab on an unproven tool. This is why the industry has consolidated into an oligopoly. The complexity of the problems requires a scale of investment that only the incumbents can afford. Furthermore, R&D is shifting from secretive silos to collaborative ecosystems. Applied Materials recently launched the EPIC Center, a $4 billion innovation platform designed to allow chipmakers and universities to collaborate on R&D under one roof. This initiative acknowledges that the physics of the Angstrom era are too difficult for any one company to solve in isolation. It represents a structural change in the industry where the lines between supplier, customer, and partner are becoming increasingly blurred in the pursuit of the next node. The semiconductor industry is often viewed through the lens of geopolitics or the stock prices of consumer-facing giants like Nvidia and Apple. However, the true power lies deeper in the stack, with the companies that build the tools, write the software, and define the architecture. Applied Materials, Lam Research, and KLA form the Iron Triangle of manufacturing, a triad whose mastery of physics makes the digital world possible. They do not merely supply equipment, they enable the fundamental scaling of technology. ARM Holdings provides the genetic code for this world, driving a shift toward energy efficiency that is reshaping the global data center infrastructure. Synopsys and Cadence act as the navigators, providing the simulation maps that ensure the industry doesn't crash on the rocks of physical reality. The interdependencies revealed suggest that the future of technology is not a zero-sum game between these players. Advancements in AI require ARM's new architectures, which require Synopsys's AI-driven EDA tools to design, which utilize Lam's cryogenic etching and Applied's atomic deposition to manufacture, and KLA's sub-nanometer inspection to verify. As the industry marches toward the trillion-transistor GPU and the commercially viable quantum processor, this symbiosis will only deepen. The barriers to entry will rise, the R&D stakes will increase, and the companies that can best orchestrate this complex dance of physics, logic, and software will remain the undisputed masters of the modern economy. They are not merely interdependent companies. They are integrated components of a singular planetary-scale machine that is building the future, one atom at a time.